This episode of the HVAC School Podcast is made possible by our cadre of sponsors. I'm not really sure what a cadre is, but I think it's like a group. So our sponsors are Mitsubishi Heating and Cooling, Carrier at carrier.com, Aeroasis at aeroasis.com. You can actually go to a form at aeroasis.com/go and get more information on their full line of products. We've talked about the Nano and the Bipolar in previous episodes. So if you want to find out more, go back and listen to those. I interviewed one of the founders of Aeroasis. But if you're at the stage where you want to find out more about their products, maybe find out the pricing or where you can get them locally, go to aeroasis.com/go. Also want to thank Refrigeration Technologies. They make all kinds of chemicals that we use every day at Kalos. It falls into the category of a sponsor that I was kind of had my fingers crossed hoping I would get for a long time because I can speak glowingly about their products. Many of you have used Big Blue and maybe Nylog, but if you haven't tried their Viper cleaners, then I would suggest you go out and give them a shot, especially the aerosol can with the Viper cleaner in it. I was actually skeptical of that because I've used aerosols before and it's sort of like, why not just mix up your own? But the nice thing about the aerosol can and the Viper is that it's a really fine pin spray. So you can spray it, especially when you're doing like a slant evaporator coil, trying to clean it in place, or you're working on maybe a reach-in refrigeration unit where you're trying to clean some grease off of a condenser. It's a really nice package for doing that, and it's non-toxic as well, which is very nice. That is Refrigeration Technologies. Find out more by going to refrigetech.com. And then finally, I have to mention UEI, the UEI Hub 6, Hub 4, and Hub 2 smart kits. Good kits of smart probes. I've already talked a lot about them. Also a podcast about that in the past that you can listen to if you want to find out more. But you can go to ueitest.com to get all the details.
Here's your host, the man who wants to be just like Jim Bergman when he grows up, Brian Orr.
Hey, thanks for listening to the HVAC School Podcast. This episode is sort of a continuation. We talked previously with Eric Mele about water source heat pumps, and this is getting more into the water side of the water source heat pump. So a lot of stuff that I don't know a whole lot about. I mean, we're going to talk about pumps. We're going to talk about all the water side stuff. And Eric gave me this long list of things we're going to talk about. So let's jump right in. Here we go. This is the water side of the water source heat pump equation with Eric Mele. You're back, Eric. Thanks for coming on the podcast.
Thanks for having me. Congratulations on number 10, or should I not mention that right now?
Yes. No, indeed. Number 10 is here. I've made some posts on Instagram and whatnot about it, and I think a lot of people think I'm joking when I say I have 10 kids, like it's just another dad joke. I guess it would be a literal dad joke if it was a joke, but it is not a joke. It is the truth, and this is it. There will be no more after this unless my wife finds a better looking man to join up with later on. But for me, this is going to be the end. So everything went well. Baby's healthy, actually, right in the other room. If you hear some squalling in the background, that's probably what that is.
All right.
So here we go. What do you do with that, right? Like I just gave you a bunch of information.
I don't even know where to go from there. Let's just get right into it.
Yeah, I have nowhere to go from there. Yeah, let's jump right into it. All right, so we're going to talk about the water loop, the water side of a water source heat pump. So I guess the first question is, have you had a chance to work on a lot of these types of systems?
Yeah, they're very popular in the South Florida area to have like a condo building. So the tenants are basically responsible for their water source heat pump, which is a packaged unit. And the building is responsible for supplying the right amount of water at the right temperature. So we're going to get to the rest of the system and get to see what happens to all that heat after you're done putting it into the water at the apartment. Or I guess there's heating mode too, but we don't use that really. But we'll cover it.
At least not where we are, yeah. Well, I guess on the geothermal side, people use that more. And again, just to be clear, we're talking about water source heat pumps here, and we're going to talk about the water side. These units are very similar to what's used with geothermal. In fact, many of them are the exact same units. But now we're talking about that side that is outside of the equipment. So we've already discussed having the proper flow rates and the proper water temperature and all that. But now we're talking about those other components. So let's start with the cooling tower. What do we got in a cooling tower? What's going on there?
That's basically where you're going to reject all that heat that you're putting into your water loop. And usually, in fact, all I've ever seen used would be an induced draft tower, which means there is a fan either drawing air through it or blowing air through it. Now, there are towers that don't use fans. They're obviously not going to be as size efficient, and that's probably why they're not used in these applications. But that's mainly what you're going to see is you'll either see a blower. It'll look like a big air handler blower blowing air into it, or it'll look like a big condenser fan pulling air out of it, or some of them are side flow. The fans discharge out the side. Some of them discharge out the top. But Same basic principle.
And how big are these things usually?
They make them as small, I believe, as you can get a 3-ton cooling tower.
Oh, really?
If you look at the ratings for them, it all depends on water flow rate and outside temperature of BTUs.
Makes sense. I mean, those equations, they're out there. I mean, talking about the heat content of water, that's been dealt with for a very long time. So I'm sure that's not that difficult to size.
We'll cover a couple different things. There is like a dry tower, which basically means there's no water in it. You're probably not going to see it too much. I've seen one, and I've actually done some piping on one. It was for the yogurt machines, which had water-cooled condensers. And this was just a big tube and fin with fans blowing across it. There was no water, and that's like a dry cooling tower. I don't know if that's the proper terminology for it, but you will see those from time to time in probably only smaller applications.
All right, so a dry type would just be like an air heat exchanger that you're blowing air over and rejecting it that way, whereas a wet cooling tower, how does that even work? So I understand the idea, the water runs down it, but what's the medium?
Well, a wet tower is open to the fluid that you're working with, so some of that's going to be evaporated. Usually, there's some different configurations, but typically the water gets pumped up to the top of the tower and sprayed out or allowed to fall, and air is blown across it. And you're going to lose some of that to evaporation, the actual fluid you're working with.
So that has to be constantly refilled then?
Yeah, you're going to have a makeup water on that, which you'd have a float assembly and you'd be constantly putting more water in. There's probably water treatment on site, and that is putting water in or putting chemicals in based on how much water that you think you're losing.
And is that the only type? They're all this like open type where you're actually losing some of your water to evaporation and heat's being transferred that way?
There's another type, and that's when your working fluid is going through a tower that's using water to cool it, but it is not open to the tower. So you're just running tubes through and you're blowing air across it and spraying water on those tubes. So you keep your system sealed. I haven't seen one used for water source heat pumps. That's not to say they're not out there, but not very popular in my area. Probably mainly due to cost and probably just not a huge advantage to not just evaporating some water. Because either way you're evaporating water, you're adding extra steps.
All right, well, the question I have is if your water is exposed like that and your air is, so we're talking about the wet open type, isn't there the potential for a lot of contaminants to get in the water that way?
It depends where your tower's located. A lot of them are on the beach, and you have strainers to deal with that and chemicals. And a popular thing that we're going to get into next about it, kind of get a little bit ahead, they do run a lot of heat exchangers external to the tower. You'll have like the tower will have its own loop, but they'll have an actual heat exchanger outside the tower.
Okay, I'm missing the purpose there. What is the purpose of the heat exchanger outside of the tower?
That just seems to be how they like to set them up. It could be due to cost. There's got to be some advantage to it that I'm not totally sure of, why they don't just use a fluid cooler like we talked about. But that seems to be a popular setup, is to use an external heat exchanger to the tower.
All right, so what's next? What else do we need to know about these cooling towers?
Well, we briefly covered the makeup water float assembly. You're going to see that in the bottom of the tower in the sump or the basin, whatever you want to call it. That's just going to have a float on it, and it's when the float goes down, it's going to let water in. When the float comes up, it's going to shut the water off. And that's going to keep your tower from running dry, always replacing the water you're evaporating.
And is it almost sort of like a toilet valve type of thing?
Pretty much, but bigger.
Okay, and do those tend to get like gummed up and have issues with sticking or not allowing the right amount of water in?
Yeah, you'll get slop in the linkage, and sometimes the water just won't shut off and it'll overflow the tower, and then you're just going to have a really high water bill. Plus, if the water is just overflowing onto stuff you don't want it to, which usually isn't the case because the tower's kind of located where that's not an issue. But you don't want to be wasting water if you could help it.
If it's open type, you have the sprayers. I mean, I guess in either case, even with a fluid cooler, you would have sprayers.
Yeah, unless it's a completely dry like the first type we talked about. But yeah, you're going to be letting water fall, and you're going to spread it out as much as possible, either using fill and sprayers to basically increase the surface area of the water. So like the fill, the water will run down it and have air blow across it. And it's just basically a fancy name for like usually plastic that is kind of shaped kind of like a corrugated material. It kind of forms like, sometimes it looks like a honeycomb, but you're just spreading out the water to increase your surface area for heat transfer. And you want to typically have that clean it with descaler as needed, or just have good water treatment and not worry about it. And there's usually going to be a strainer on the outlet of the tower, almost always. So people miss that because you'll have bad water flow, and you'll see it'll come from somebody didn't realize there was a strainer in the tower that got plugged.
Okay, so that would be like the equivalent of a dirty condenser coil almost, because it's going to affect the amount of water that's flowing through your heat exchanger, which is your condenser. But in this case, instead of a dirty condenser coil, you've got a strainer that needs to be, what do? You just remove it and clean it? Is that the typical procedure?
Exactly. You just clean it off. And it would be more like a restricted liquid line dryer, but same effect. You're going to reduce your water flow, and nothing good happens when you do that.
Drives your head pressure up, all that stuff.
Yeah.
Talk a little bit more about the heat exchanger configuration and what you're exchanging. So it's a heat exchanger. What are you exchanging it to?
So it's usually a water-to-water setup where you're going to just have your tower water, which is open to the air, exchanging heat with what would be your closed loop on the other side of the heat exchanger, which is not going to be open to the air. And that keeps the contaminant levels way down when you do it that way. That's typically why they're going to do it.
You talked a little bit about the ocean water type heat exchanger, which is an interesting heat exchanger setup as well.
Yeah, you can also not even have a tower at all. If you have a body of water where, according to local laws, I guess it would be let you use that water to exchange heat with from your building. And you can use seawater, maybe a lake or another large body of water to exchange the heat with rather than having a tower at all.
I used to work on a decent amount of these in our market, and they called them, well, there was the brand Florida heat pumps, but we used to actually just call them that. It became almost like a generic name we would call them, even if it wasn't a Florida heat pump. And most of the ones we saw were actually just open loop systems. So they would just pump water out of a lake, and then it would run through the heat exchanger or through the condenser, and then they would just pump it out and dump it in the yard, or in some cases dump it back in the lake, some cases a little short of the lake, and there'd be like a little trench running back, all these sorts of things. But then Florida, specifically the water management districts, cracked down and really didn't want us using lake water, even in most cases groundwater, to do this, which is, there's several reasons, but one of the reasons why these types of systems aren't very popular where I live anymore in residential applications, and then even geothermal has its own set of problems in Florida. So yeah, there's a lot of different ways that you can reject this heat, but on these larger commercial applications, it seems like one of these types of towers, the cooling towers that we talked about, either the dry where there's no water and it's just air going across, so it's open, which would be the most common, or the fluid cooler type where you're running water across a sealed loop are going to be the most common type of cooling tower. And then your heat exchanger, you've got to be exchanging to another water source.
Exactly. And I've seen those residential systems you're referring to, but they weren't very common, at least in my area at the time that I saw them. But yeah, they might still exist.
Yeah, and the issues that we had with pumping water, and I mean, as you think about pumping in lake water, I mean, now that's water with a lot of crap in it, and so you got to worry about filtering it and straining it and all that, and you get a lot of issues with that because you have no real control over the quality of the water. You can't treat it with chemicals, obviously. So at least in this case, you're controlling the type of water that's going in and out of your equipment. You're using chemicals in it. And let me ask you that question. So what type of chemicals are used? Obviously, you got to be really careful to control the pH so that way you're not damaging the internals of the water source heat pump, right?
Usually we see third-party contractors that specialize in that type of thing deal with the water treatment aspect. I've never directly dealt with any of it. That seems to be pretty common. There's companies, and that's pretty much all they do is water treatment for those towers.
Have you ever seen issues with heat exchangers failing inside of water source heat pumps that may be due to chemical problems?
I don't know that I could prove that it came from chemicals, but you definitely see that they plug up. I have one account, for example, I think they went without water treatment for a long time. And every time I go to their tower, we have to go there every 3 months and take the top off this tower. And it pumps the water up to the top, and it goes through all these little plastic cones, for lack of a better description, to spread out the water. And they plug up with huge pieces of calcium scale. I'm talking like big, like gravel pebble sized pieces that are coming out of the pipe, and they're shaped like the wall of the pipe. You could tell they've been stuck on a pipe for a while because they've got that kind of half pipe shape to them, where one side's really smooth where it detached from the pipe, and the rest of it just looks like the chunky scale that you see.
Yeah, got it. And so that's kind of on the other side. If you don't have any treatment, I mean, it's the same. So like in pool heaters, this is where this is coming from. We work on pool heaters a lot, and it's sort of like a water source heat pump, or is a water source heat pump. And you see issues with the heat exchangers failing, especially when they used to be made of cupro-nickel instead of nowadays they're mostly made of titanium. You would see them fail a lot, and it was often blamed on extreme pool chemicals. But I guess in that case, they're using pretty heavy-duty chlorine and whatnot for swimming, and they're probably a little more gentle when you're dealing with cooling tower treatment.
Yeah, I would imagine so.
All right, and now the next thing on the list here is pumps. So what's the story with pumps? How are they piped in? How do they function?
Obviously, you're just using a pump to move the water where you want it to go. So you're pushing water throughout the system with pumps. Typically, the only pumps you're going to see today are going to be like the centrifugal type pumps. That's pretty much all I see anymore. I know like back in the day they used to do different kinds, but that's all we see now. And you might see a couple pumps piped in parallel. And pretty much every pump you're going to encounter has a strainer right before it on the back of the pump. So you'll see like a blind flange at the back of the pump. It'll look like a T with nothing coming off the side of the T, and there'll be a strainer in there to protect the pump.
And obviously, everything in the circuit is on the positive pressure side then on these circuits.
If your pumps are on the ground, you can start to see like 0 PSI on the suction side, or actually, depending on where you're measuring in the system too. Like if you have a pump on the ground and you measure on the 4th floor, your suction side could be like 0 PSI. Or vice versa, if your pump's on the roof. It depends how high the pump is above everything else, but you can see 0 PSI on the suction side, and it can be perfectly normal.
I like the way that Dan Holohan talks about pumps, because we get confused sometimes when we're thinking in terms of air conditioning. We think compressing a vapor, but in pumps, you're circulating. You're not compressing because liquid is largely incompressible. But if you think of a water circuit, a water loop, as being like a Ferris wheel, where in the Ferris wheel, it's not like you have to have the force to pump the water all the way around in the same way that the motor in the Ferris wheel doesn't have to move the Ferris wheel all the way around in a circle, because the weight on one side balances out with the weight on the other side. So if you have a bunch of people on one side of the Ferris wheel, it balances out with the other side. And so now all you really have to do is just the friction of the wheel itself. That's really all you're doing, is the motor's just driving against the friction. And the same thing is true in a water loop. It's not like you're having to have all this force to pump it all the way from the ground all the way up to the 4th story, because if you imagine the other side, well, now it's pulling down the other way.
Exactly.
Sort of a balance of forces there.
The pump just creates a pressure difference at the pump. It doesn't really care about anything else.
Just enough to keep it flowing.
Exactly.
All right. And then is there anything that you commonly see? So you got to watch the strainers, but do you end up rebuilding a lot of pumps, or anything that you typically see or look for in pumps?
Bigger pumps, we have a subcontractor we use that can get them rebuilt pretty quick, because that's usually what happens is these buildings are going to call you and they're going to be like, there's a bunch of water coming out of the pump, and it's usually like a shaft seal. So we use a contractor that's all they do is pumps, and we'll either take the pump to them or they'll actually come remove it if we want them to. And they can usually do a 1-day turnaround. We can do it that way. Or if it's a smaller pump, you just can replace the pump if it's not, doesn't make sense to spend the money to rebuild it.
Yep, we did a lot. Shaft seals are something that we did a lot when we did pool pumps. We don't do them anymore just because there's not any money in it. But we actually rebuilt a lot of pool pumps for a while, replaced the motors, and then we would always replace the shaft seals at the same time, because those would always cause us issues in the process of replacing the motor. So
yeah,
they are finicky little things. And obviously, whenever you have a shaft emerging from something that's moving a fluid, it's a likely spot for it to leak.
Yeah, and alignment on pumps is a good thing to be aware of. I know I sent you a picture the other day of a customer who refused alignment. They have newer couplings, which aren't as bad as the older ones. They're called Duraflex couplings. At least that's what the brand name that's used a lot. And they're very tolerant to misalignment, but that doesn't mean that bad things aren't going to happen to other things when you have a misaligned pump. Your bearings are still going to take a beating. And then the older couplings that we'd see, they're called Lovejoy couplings, or at least that's what I've heard them called, where you have, it looks like a spline, and it goes in between two cups that have kind of the shape of the spline cut into them. That's the best way I can explain it.
Kind of envisioning it, I guess. I mean, you saw a lot more failures. They had a lot lower tolerance for being out of alignment.
Yeah, they have a much lower tolerance for being out of alignment, but alignment's important either way when you're talking about pumps like that. Some of them are direct. The motor shaft goes directly into the pump and you don't have any sort of external coupling, but the ones that do, alignment is a really important thing.
I get a lot of questions about like belt alignment and motor alignment and that kind of thing. Issues with pulleys. And a lot of it is just common sense. Like you can have fancy tools and for alignment and all that, and that's great, whatever. But most of it is you just have to be thoughtful and use common sense and pay close attention. And then you're going to avoid a lot of these problems. If something's misaligned and you just leave it because you're like, yeah, forget it, whatever. There's always going to be ramifications from that.
Yeah. And as far as having fancy tools, all you really need, you can do a lot with just a straight edge. You can do a lot just with that. You can pretty much do everything you need to do. Now, obviously, the more precisely you're aligned, the better, but just a straight edge can get you where you need to be. And a cheap little caliper in conjunction with that, you can get a lot, you can get really close.
Yep, absolutely. All stuff you can get at Harbor Freight if you're so cheap that you want to go that direction, but it doesn't require $1,000 alignment tools. Although, again, I'm not knocking it. There's nothing wrong with using laser alignment or whatever, but it's not necessary. A lot of it's just being thoughtful and taking the time to make sure that it's right.
Exactly.
All right, next is boilers. So sometimes you got to heat the water as well. So what do you run into there?
So in order to get effective heat out of a water source heat pump and prevent pipes from sweating, which is another big problem, you got to have a way to put heat into the water so that your heat pump can have somewhere to take the heat from to put it into the space. Typically, in South Florida here, there's not a lot of care taken to make sure the boilers are put in right or working right because we don't use heat that much, but I do know a little bit and have had to play with them a little bit. You're going to see them piped in, at least how they should be piped in, because I've seen them not, is in a primary-secondary configuration, which means that both pipes going to the boiler, the inlet and the outlet, are going to come from the same pipe with two closely spaced T's. And I think there's a certain distance they want those T's. You want them really close to each other, and you don't want them more than like 3 or so pipe diameters apart if you can help it. And the boiler is going to have its own circulating pump to circulate that water into the loop. And a lot of these boilers are gas and 80% efficient, so you really don't want 60-degree water hitting your boiler. You want to keep your incoming water to 130 degrees. And you want a mixing valve to achieve that, to just let the water, it's going to mix some of your discharge boiler water back into your intake water into the boiler to keep it above 130 and like keep your discharge usually like 30 degrees above that or more, whatever you can get away with, so that you don't ruin the heat exchanger. But I haven't seen a lot of issues with that because we don't run them often, if at all, in Florida. A lot of times they get put in and they never use them.
Yeah, especially in commercial spaces where you may not have as much thermal exposure. You've got condo units and whatever, and so you've got condos on top and on the sides, and you don't have quite the load. And in our area, we have some boilers and these applications, but again, they don't even get run much here in Central Florida, other than just the obvious things to think about, like what you mentioned. There's obviously even more obvious things that all apply to regular furnace stuff. And when you got an 80% machine, you got to think about combustion air, make sure that it's got the appropriate amount of combustion air. The biggest danger would be something that was never set up properly in the first place that then is possibly leaking unspent gas or carbon monoxide, those sorts of things. So that would be my main encouragement if you end up getting thrown onto a boiler and you're not really a boiler tech. Just make sure that it's safe. Make sure that it's not allowing ambient CO2 to get into the space. Make sure you check all of your connections, all those sorts of things, so you don't have unspent gas. All those obvious steps that should be taken and are very obvious to a lot of our listeners up north, but to those of us who don't work on many of them, sometimes aren't as obvious as they should be.
Yeah. And something I've noticed that I've run into, they don't get a lot of maintenance. So you'll see like the temperature and pressure reliefs get clogged up with loop water scale and need replaced, and flow switches. So your boilers, a lot of them aren't going to start because the flow switch is probably gummed up, and the TNP, when you go to test it, is not going to do anything, which in an open loop, probably not such a big deal, but you still want it to work. You don't want to melt down the boiler. So definitely look out for that.
Yep, for obvious reasons. Boiler meltdown does not sound good. I watched the Mythbusters episode where they blow the water heater through the roof of a 2-story building when the temperature and pressure relief sticks. So you definitely don't want that sticking.
Yeah.
All right. So next, tower bypass valve. What's that all about?
So that ties into heating the system. So if the water temperature drops low enough, you don't need to run water through the tower or run tower fans. There's just no point. You're just wasting money if you're running the tower fan, and you can keep your loop water temperature high enough that you don't need to turn your boiler on just with that alone for quite some time, if not all of the time. In bigger systems, you will see that. They're just going to start bypassing tower water when it drops below a certain temperature. You can usually do it like at 75 degrees. You can just start bypassing the tower. And maybe it's a constant on-off valve, or sometimes they modulate depending on the control setup.
So in some cases, you may have a modulating valve that's still using some of the tower, but not is running as much water through the tower. That's the idea?
You can, yeah. When you start really reducing tower flow rates, you're really not going to get much out of the tower after a certain point. But it all depends on what they put in. All of this stuff's kind of built up in the field.
Right, yeah. It's not like it comes in a box that you just install it the way that it comes. You have to decide what it is that you want. And a lot of it has to do with what was specified initially by the engineer who set up the building. In a lot of cases, that's going to end up, you may have a little over-engineering things that may not really be necessary for the climate. We see that in a lot of cases. And like in large commercial refrigeration, they set things up as if we were in the Arctic North or something. And so, yeah, I get that side of it.
Well, they wanted to pay an engineer one time to design something that would work everywhere. So that's what happens.
Well, not only that, engineers love to specify things, right? I mean, hey, that you're in the business of specifying things. And if you're just something cool or new, then by golly, you want to throw it on your plans because it makes it seem like you're doing something important. It sounds like I'm bashing engineers. I'm not. It's a necessary thing, not a necessary evil. But there are some cases where things get a little over-engineered.
Yeah, for sure.
And I'm sure we've all seen it if you've been in the field for any amount of time. All right. And so next, expansion tank. I just want to add quickly on expansion tanks. Again, for those of you who work on water systems a lot, this is very obvious, but to some who have not worked on many, with an expansion tank, some of you may have like a well at your house, and so you see expansion tanks. But don't get the idea that that air that you're putting into an expansion tank is somehow directly interfacing with the water. There's actually a separation there, and that expansion tank is allowing for that change in volume of the water with thermal changes or with changes in pressure without having it act against the pipes or against the walls of the actual system itself, because that could cause some major problems. So don't get confused about that.
Or surging through the pumps.
Well, exactly. And I was going to let you talk more about that. So what do you have to know about expansion tanks to work on these systems?
We pretty much already covered all of it. It's just a cushion of air to give a margin of safety for components in the system. And sometimes they're an air bladder type where the air is actually in like a sealed, think of it like a balloon, and sometimes there's just an open amount of air in the tank. But it's not meant to go anywhere. It's meant to stay right where it is and just be a cushion.
Yeah, I guess I said that wrong. Yeah, so there is an interface in the sense that the water can be touching the air in some configurations, but it's still stationary. It's not like it's circulating through the system or something. It's just there in that tank acting as that cushion. And so when you see cases with water hammer or whatever, what do you notice? You just notice that like slamming noise? What do you actually see?
I haven't seen a lot of it happen at the time. I went to a job site where it had happened afterwards. And it was something where we just added piping to an existing system, but we did see a pipe break due to water hammer, but it wasn't like a continuous thing. They had a ton of power issues, and I'm not sure if they had a proper expansion tank or not. That was just there to make a repair. They had another contractor that maintained that end of the system. So I really haven't seen it too much in person.
There's a lot of percussive force that occurs if your expansion tank isn't set up properly. So sometimes if you have like the bladder type system and the bladder leaks, or the Schrader core that you're using or whatever you're using to get the air in the system, if that leaks and then you don't have, it's no longer acting like a pressure tank like it's supposed to, then that can cause all these sorts of problems.
Definitely.
All right, so let's talk about air in the system. And so this isn't expansion tank air. This is actually air that's circulating with the water. What do we do about that?
Yeah, we want to minimize that as much as possible. So in properly designed systems, you'll have air bleeds where you need them, but there's a lot of systems out there that just simply don't have them. They've either been removed or they never had them to begin with. But it looks like a little cylinder that usually comes off the top of the pipe, and it almost looks like it has a Schrader valve in it, but it's not really like a Schrader valve that you'd see. You can't just take one out of the truck and put it on. It's going to let air bleed out, but not water. It's got a little like float in it. That can bleed a limited amount of air. That's not going to effectively bleed a ton of air off the system. So if you had the system open, you're better off to pull a couple of those off and just, they usually have a ball valve under them if it's a well-designed system. So you could pull the air bleeds off and use the ball valve to purge off a ton of air when you refill a system. But they also will probably have a air separator tank on a closed loop because they don't want a bunch of air to hit the pumps. So it's kind of a margin of safety for that. So you don't have a big rush of air come back and just hit the pumps, and then the pumps become airbound, and then bad things happen to the inside of your pump because they're cooled by the water that's coming through, and they'll heat up and they'll destroy impellers and bearings and that type of thing.
I don't know that I've ever seen an air separator. What does that look like?
It's just going to be like a really big version of the ones you see on top of the pipe where the water comes in and has a space for air to go to the top, and then it's going to have an air separator at the top of it, like usually a large diameter one. Because they have the air separators in different size, but it has like a space that a bunch of air can go to if needed.
Because obviously the air is going to, when the water's allowed to run through a volume where there's a gap, the air is going to travel to the top.
Yeah, so you usually see the piping comes in. The piping might come in at the same height on both sides, but there'll be space above it for air, or the pipe might come higher on the inlet side than the outlet side. It's different configurations of them.
All right, so from a control standpoint, what are the controls usually like on these?
Pretty much how we talked about before, how this is a built-up system. It's all like components that are assembled in the field. Your controls can range anything from just basic to variable speed. So we'll go with the basics first. Something techs might not be used to seeing is a motor starter, which is a fancy name for a contactor that has an overload relay attached directly to it. So you'll see a contactor, and then usually there's like 3 prongs on the overload relay. Sometimes there's wires, but usually not. Usually it's directly mounted to it. And it's going to be able to interrupt the contactor based on current. So they're basically little bimetal heaters sized for the load. And if you get like a phase imbalance or an overcurrent, it's going to shut it down.
So for guys who are used to working in residential or like commercial, you may hear a motor starter and you may think, because I did for, I don't know, several years before I started working on larger equipment. When I heard a motor starter, I thought that was like a start capacitor for a 3-phase motor or something. I don't know what it was, but it's a big contactor usually, and it's got a overload in it, like Eric said. In a lot of cases, when you have a starter, the motor itself may not be internally overload protected. Do you see that on these pumps? Do they usually have an additional?
Bigger motors, a lot of them aren't internally protected, but that's kind of the idea why it kind of necessitates a motor starter.
Right. So you can't just take a motor starter and replace it with a normal contactor. Otherwise, you've got no overload protection. And you need to have specific overload protection for every motor that's connected. I mean, it stands to reason that obviously if you have circuit breakers or things like that, they may be running multiples. In this case, it probably has its own circuit breaker. I'm not sure. But if you're working on even on large AC equipment, you may have multiple motors, multiple loads inside that unit. And so they each all need their own overloads for each device. And that's what a motor starter provides. And you need to set that in specifically for that motor that it's working with. And obviously, if it was originally set up, then it may have a setting on it, but you want to check, even if you were to replace a motor starter, to make sure that that is an appropriate setting for the motor that you're connecting to. Because, say, for example, somebody went and changed it because they were sick of the thing tripping, which is the sort of thing you see a lot out in the field. It's very possible that the old one was set too high, and that may have led to failure. So you want to make sure that you set it in appropriately.
Exactly. You definitely want to size it for the motor you're using. And some of those motor starters will lock out. Some of them will automatically reset. And some of them you can actually pick that. There's a brand, it's called like WEG. And there's a little dial on there, and you can make it auto reset or not. Depends on your application, right? How important is it for that motor to run? So you're going to have to determine that if you want it to automatically reset.
Right. How important is it for it to run, and how important is that it doesn't fail? Because obviously if you've got one that's auto resetting all the time, you're more likely going to burn up your motor, and then you're going to have to deal with that. So there's a couple different considerations there.
If you can, you might want to put a delay timer on if you're going to leave it on auto reset. That way you can auto reset, but then have a delay so that it doesn't immediately come back on. And if I remember correctly, I think some of the WEG ones there, it does have a delay built in, but you'll have to look at your specific device. But something that people might not used to be seeing too is you could have a lot of line voltage controls going on. Like a lot of those motor starters are set up as such that the coil voltage is the same as the applied voltage, and they'll just have a jumper to one side of the coil, and then the other side will go through your handoff auto switch and your overload relay auxiliary to shut the contactor off, and any other external controls you want to add. So something to watch out for. And while we're on the subject, a handoff auto switch, if you have external controls mounted to it and you put it in auto, when the external controls let it come on, then it's going to come on. If you put it in hand, it should run continuously. And if you put it in off, it should turn off no matter what the external controls are telling it to do.
So auto's external controls, hand is like a manual override, and then off is just completely off.
Exactly.
That's the typical setup. And then what about variable frequency type setups?
So if you want to save energy, a lot of applications will use a drive to change the speed of the pumps and the fans, depending on the application. Usually if you have a closed loop and you want to change the speed of your pumps, you really have to have a way to shut off water flow through units that aren't active in cooling or heating. So they'll have a 2 or 3-way valve on them, usually a 2-way valve, that's going to shut it down and reduce your need for water flow. And then you'll reference a differential pressure to slow your pumps down.
That was actually a question that I had that I forgot to ask last time, is that there is actually a way then to shut off so you're not just constantly flowing water unnecessarily through all these units that have no call.
Exactly. And usually on a tower fan, you'll do that too, and you'll set it up so if your water's getting too hot, you bring the fan up to full speed. If it's not, then you can drop fan speed or even shut fans off, which is definitely feasible. You'll save a lot of money If you slow a motor down from 100% speed to 75% speed, it's like uses 50% of the power, something like that, I believe, which is perfectly reasonable to do.
Do you find that even when they have them, though, that a lot of times they're just bypassed?
I think the worst thing that they've ever done is put a bypass on a drive, because I have a customer with 6 of them that they won't replace, and they're running 6 drives in bypass. And the worst part about it is the system was not designed for constant volume water. So every indoor unit, every water source unit was supposed to have a 2-way valve on it. Well, contractors have since gone through and removed all the 2-way valves. So now they have water flow issues. So now they're at the point where you're talking about replacing drives and adding valves to hundreds of units to get your stuff to work properly. Unfortunately, this is not uncommon.
Yeah, and that's what you run into a lot. I've seen it in a lot of grocery stores where you'll have variable frequency drives, or freak drives, as a lot of guys like to call them, because that sounds really cool. We got a freak drive on it, on their condenser fans, on refrigeration, and you see those things in bypass all the time. And it's just so sad because there's so much money that was spent initially on trying to save money on power. And like you mentioned, they were designed to have that variable frequency drive in place, and then you just completely disable it. So it's a bummer. But
the thing about it too is, okay, on a refrigeration condenser in a store, yeah, you're wearing your fans out. If you have wintertime, you might screw with your low ambient operation. But when you're talking about flowing water through pipes, you're also wearing out your piping. You're wasting a lot of effort. I mean, it's not going to be fun to repipe these buildings.
Right. If they weren't designed for those flow rates, they weren't designed for that constant flow like that, then yeah, you are going to cause a lot more trouble for yourself in the long run.
Yeah, in the long run. And one thing I don't really see too often, though, is the tower loop pumps. They don't usually have a drive on them because they just want a constant volume. Sometimes they do, but a lot of times they don't. They don't worry about putting drives on those tower pumps because they're not really changing the water flow rate through the tower enough for it to make sense in a lot of cases.
So what else? What are we missing? Anything we missed?
One thing that I put in the wrong order on the list, this is my fault. We probably should have gone over Aqua stats before drives, but if you're cycling a motor starter or even just a regular contactor for a tower fan, you're probably cycling it off an Aqua stat, which is just a sensor bulb in the water and a relay that letting that fan run or not run based on the temperature of the water.
So it's almost like a simple refrigeration control, but it just instead of embedding it in the coil or something, it's just in the water.
It'll look like the air probe that you see in a walk-in cooler. In a lot of cases, everything will be very similar about it. You might even be able to use one for that purpose. Not totally 100% whether you want to drop that bulb in water, though.
Are they made of copper? Is that what they seem to be made of in this application?
Maybe it's got a coating. Usually they look like they're made of copper or a copper alloy.
Yeah, you're probably safe then.
At least for a while. It'll work until it doesn't.
You'll find out, yeah. Let us know. Sounds good. So there we go. There's our introduction to the water loop, the water side of water source heat pumps. So yeah, I appreciate it, Eric.
We got to cover programmable logic controllers real quick.
Okay, yeah, let's do that.
If you're looking to modulate frequency drives, you have to have some kind of analog signal to send to your drives and something to interpret the signal from your sensors. So there's really simple ones that Honeywell makes that I like. I believe it's like the T775 or something. And there's obviously way more complicated ones, some proprietary ones, like the Johnson Controls FX10s, FX05s, stuff like that. You'll see a train tracer is another one that can be configured for this type of control. But you're basically looking at sensors, deciding what you want them to do. Like, okay, when we see the water temperature, we're going to target 85. So at the water temperature is at 85, we're going to slow the fans down. When it gets higher than that, we're going to speed the fans up, right? Or you're looking at differential pressure and trying to maintain differential pressure based on a signal that you're sending to your drive, which could be a standalone controller in either case, or you could have one controller that's taken all this information and given it to a bunch of different drives. So you just got to look at how it's set up in order to achieve what they're trying to do.
What type of drives do you generally see? Danfoss drives, or what are you generally working with?
Danfoss, Train, which I believe the older Train drives are Danfoss drives, ABB, Yaskawa, Honeywell's even making them now.
Oh, really? Okay, I didn't know that.
Maybe somebody's making them for Honeywell. I think Hitachi makes drives. There's a bunch of companies that make them. Who knows what you'll see out there, right? But those are some major ones that you might run into.
And like you said, these are built up systems. So you're taking from here and there and you're building a control system from scratch, usually based on a specification that was originally laid out. Or if somebody came in later and maybe even a contractor may have done an upgrade or a retrofit and brought in their control system. But yeah, you'll see a lot of different setups. And generally speaking, at least in my experience, when you're working on a built-up system, it's going to take you a little bit to kind of get the full picture of what's going on or what the original intent was. And that's why it's nice to, at least with this sort of work, you generally want to work on a contract basis where you're going back regularly and you know the system that you're working on versus just getting thrown into the middle of it, because it can be kind of messy to try to get caught up.
Yes, it can. That's definitely for sure.
All right, man. Well, cool stuff. Yeah, I appreciate it. We'll be talking again with Eric very soon, I'm sure. But that's a brief overview of these sorts of systems. If one of you out there are listening to this and you work on these systems all the time, feel free to chime in and give us your feedback. In fact, I'm going to play a clip right now that I got on Facebook. And I don't think he originally intended on this being played on the podcast, but I asked if it was okay, and he said it was. Andrew Greaves had some thoughts about our last podcast with water source heat pumps and a little tip that he has for finding the presence of leaks inside of a heat exchanger. So have a listen.
Oh, nice.
Hey, Brian, it's Andrew. Just listened to the water source heat pump intro podcast. Good job, both of you. I just couldn't help but inject my own little tidbit. If you guys have a follow-up episode about troubleshooting or doing repairs on these. First of all, we have quite a few of them as well in my area. However, I was interested to hear about the cap tube. I've actually never worked on one that didn't have an expansion valve. But anyways, one thing that you'll run into a lot is leaks. The piping is so tight in there that you get a lot of rub outs, and they can be a nightmare to repair depending on the location of the unit. A lot of times you got to completely disassemble the cabinet to even get at something, and even then it's still hard. But what do you do if your leak is in that coaxial coil? That's a very real possibility. I've had probably 3 in my short career that have been leaking. One way you can rule out the coaxial coil as a leak suspect is to take loose your water lines, valve them off first, take them loose, drain the water, then take rubber gloves and put them over the inlet and outlet fittings on the heat pump. Just take some electrical tape or rubber bands or something and fix them on there. Then go ahead and charge your system up with nitrogen if you're doing a nitrogen pressure test. Go to lunch, come back, and I promise if you've got a leak, those gloves will be inflated like balloons. And I've found 3 leaks in the last few years that way. So it's a great way to do it. There's no real other way. I mean, you can take an electronic leak detector, but frankly, they're so small, those heat pumps, it's not very definitive because you could easily be picking up refrigerant from somewhere in the cabinet. So this is a surefire way to kind of just using things you have in your van, a little unconventional. Just thought I'd share it. It's always worked great for me, and maybe it can work for your guys too down the road. So anyway, great episode. Talk to you.
All right, well, thanks for listening to the HVAC School podcast. Thanks to Eric for coming on. And I want to mention real quick, because it's been a while since I've thrown this out there, that if you've got something you want to talk about on the podcast, then shoot me an email. My email is Brian, B-R-Y-A-N, at hvacrschool.com. I'm always happy to talk to people. And a lot of people kind of have this sense that, well, I'm not an expert. I couldn't come on a podcast. I'm not an expert. Hey, let's be truthful here. All of us are experts in some things. An expert just meaning that we know more about it than a lot of other people, but none of us are experts on everything. And I am certainly no exception to that. I'm not an expert at most of this, frankly. HVACR basics, I've done a lot of training on it, but all this stuff that Eric was talking about today, I mean, I've worked on these systems a few times. I mean, it's not regular. I always learn a lot on every podcast. So if you have something that you wish that I would talk about, well, then by golly, you may be just the person to come on and talk about it. And the way to do it is just make a little outline so you know what it is that you want to say, and then call me up and we'll get together and record a podcast. It's a lot easier than you probably think it is. So you have that open invite from me right here. And again, that's Brian, B-R-Y-A-N, at hvacrschool.com. As always, you can find out more about all of the different worlds of HVAC School. That's a little bit of an overstatement. All the different content on HVAC School by going to hvacrschool.com. You can hear the other podcasts by going to bluecollarroots.com. So yesterday, I was walking into a store and a clown held the door open for me. Thought it was a nice gesture. All right, thanks for listening, and we'll talk to you next time. on the HVAC School Podcast.
Thanks for listening to the HVAC School Podcast. You can find more great HVACR education material and subscribe to our short daily tech tips by going to hvacrschool.com. If you enjoy the podcast, would you mind hopping on iTunes or the podcast app and leave us a review? We would really appreciate it. See you next week on the HVAC School Podcast.